Hi everybody. So I'm Aaron Levine, I'm from Rakuten Institute of Technology, Boston, and today I'm going to give a talk about one of the sort of fundamental advancements in technology that has led to being able to process massive amount of data, and in a couple of words, that is the power of parallelism. So one of the biggest problems sort of facing every business out there in the current climate is sort of too much of a good thing. There's quite simply too much data. There's entire waves of data. Basically, there's too many images, there's too much metadata, there's too much data on how people are visiting sites individually, and there's especially too much text. So to give an example of that, if we take our flagship site at Shiba, we have, for instance, thousands upon thousands of merchants using the site every day to list their products. There's millions upon millions of users using the site. I've seen the exact numbers if you just attended the keynote a little while ago. There's hundreds of millions of products overall, and there's billions upon billions of words between the titles, the descriptions, the metadata for each of those products and each of those. And that's just on a single site out of endless numbers of sites out there on the web. It's the same thing basically for any other internet business out there. We have technology and we have engagement, and to have databases with millions upon millions of data points of all shapes and sizes, all different kinds, and whether it's Rakuten or Google or Facebook or Baidu or an eBay or several hundred other sites you can say out there, there's always going to be that amount of data. And so this leads to one big problem, which is the problem of curation. How do you curate all this data exactly when you have millions upon billions of pieces of it? How do you detect, for instance, if you want to know if someone's posting a piece of inappropriate content that you don't want on your site? What do you want to do if you want to be able to group similar types of products or similar types of pages together? How do you want to do transferring of products between one site or another, for instance, if you want to be able to have a global reach for your data? So just to give an idea of one solution, something some people often go to is the mechanical Turk. Here's a picture of the mechanical Turk, sort of the idea of it, which is basically to say that we're going to have humans, for instance, do a classification task. So let's take a simple one, for instance. Let's say that we want to find if a post is inappropriate, that first example we had a second ago. Just a simple yes-no binary choice. Is it inappropriate or not? And let's say we have 100 million records, and let's say it takes about 5 seconds a piece for a person to decide on that. Look at the text and to decide, is this appropriate or not, yes, no. Well, it turns out if we take that over one data set of 100 million data, that becomes 200,000 man hours about, just to do that one task. So that's over 15 hours of work for an individual doing it 24 hours a day, 365 days a week. And what's even worse about that is, again, that's just for a yes-no task. That's not for what type of product is this? Is this a hat? Is this a piece of electronics? Is this a shoe? Is this posted by a male or female? Hundreds of different things like that that are far more complicated than a binary choice and may take much, much longer than 5 seconds. And that's far from the largest data set that anybody necessarily has in a business. So then, what exactly is the solution? Well, if you ask a lot of people out in the industry today, a couple of keywords keep coming up these days. Things come up like machine learning, deep learning, cloud computing, microservices. And again, sort of I said at the top of the talk, the one thing that sort of combines them all together is this idea of parallelism, which is basically this big trend of technology that I feel in some ways is sort of the secret sauce that ties these all together. Things like having a CPU going from a single core with one thread on it to having a CPU with 4 cores and 4 virtual cores. Now we have 8 threads overall for any individual laptop like the one I'm talking on right now. Or having a unique architecture for GPUs that have hundreds or thousands of cores apiece. Or things like MapReduce frameworks or so forth. That are able to do tasks that are spread between multiple machines. So again, you go to the, sort of makes sense why this is the case. If we have 4 to 8 cores of compute threads that can do 4 to 8 tasks at once, now we can do a job 4 to 8 times faster if we can break it up into packets. If we've got a computer with industrial-grade server CPUs in it, for instance, as opposed to something you might have in a standard laptop or personal computer, now we've got 50-plus cores that are each doing those individual tasks at the same time, 50 times faster or more. Then if we take even sort of the lowest level of a modern industrial-grade CPU, something like a NVIDIA Titan X, for instance, now we're doing that about 3,000 times faster, because that's the number of cores we can start to split tasks across. And if we have 10 of those servers working in parallel, and we have something that can, in normalized, fault-tolerant way, distributed between 10 different of those individual, GPUs, now we can do it 30,000 times faster than we had before. So to illustrate this, let's start by taking a look at machine learning, for instance. Let's take a look at a particular library that's popular these last few years, XGBoost. So for instance, if you go to a data science site like Kaggle, for instance, where people are doing competitions where they're trying to basically do, classification tasks or identification tasks or extraction tasks of various sort for large businesses, and put this up to sort of get ideas for technology and people that they want to bring in. This is one of the big libraries that you see a lot of people using who submit to these sort of competitions. So why exactly is this? Well, it's not exactly because of the algorithms themselves. In fact, the algorithms that make up the XGBoost library itself aren't anything revolutionary or particularly new. Basically, they were all designed decades ago. Any individual piece that sort of makes up the different parts of the gradient boosted trees that make up this library. So for instance, decision trees, the basic version of this, is first published in a paper in 1975. It's decades and decades old. And random forests was sort of the next step that gets us to the gradient boosted trees from 1995. And the actual idea that's being used in this gradient boosting was created in 1997. So even the newest part of this is 20-year-old algorithms, 20-year-old technology in a way. Basic idea of the concept isn't super complicated itself either. It's fairly straightforward. It's basically we have branching trees of decisions. Yes, no, A, B, C, things like that. So for instance, does a piece of text have the word hat in it or any other individual word? Or do we have a piece of metadata that's more or less than the year 2000? Is it before or after the year 2000? Things like that. And at the bottom of these decisions, after you make all these individual decisions going down the tree, you have a label for it. Is it just saying, is it an appropriate post, for instance, or what type of product is this, or so on. So for instance, in this image of a human-made tree, it's sort of making these decisions at the bottom, deciding how much individual money will be made or lost based on these particular decisions that were made. So no, saying that those parts are simple, the actual thing, the reason that people use this so much is because XGBoost takes advantage of parallelism. Sort of the secret sauce of XGBoost that made it so popular is because it doesn't just do gradient boost in a standard fashion. XGBoost subdivides the data into simultaneous testing, basically, of every potential decision point in a tree. So basically, individual parts of the tree are assigned to individual threads. In fact, the original technology that this was based on was by a PhD student who wanted to do experiments into seeing if you could do a sort of MapReduce framework to subdivide and then recombine matrix calculations. And this allowed it to then be spread to doing gradient boosted trees, where instead of doing it the way you do random forests, where you're doing these decisions, you're basically training a bunch of different trees in parallel. You instead train individual decisions on these trees, and then each of the subsequent trees learn from each other. So same idea, same sort of benefits of multiple threads working in parallel is also what's led to the growth of deep learning as well. Namely, because deep learning algorithms can be run using GPUs that have customized architectures that have hundreds of cores instead of just the dozens max that we again have on CPU. So once again, the neural network libraries that have become popular, much like XGBoost for instance, are decades old. So two of the big sort of deep learning networks you'll hear about today, convolutional neural networks and recurrent neural networks, were both made in the 80s, 1980 and 1982 respectively. So again, decades old. Instead, sort of the growth of deep learning that's happened over the last few years has mainly been because it's powered by a piece of technology that was developed in a completely different industry altogether. GPUs were historically, graphics processing units were made as chips to render multiple objects in a graphics setting in parallel. So simulate lighting on lots of leaves on a tree, or simulate how gravity affects dozens of different objects at once, things like that. But as it turned out, to do this, the GPUs were set up to be exceptionally good at doing multiple matrix calculations in parallel. Basically, tensors or multidimensional matrix calculations, as you might hear. And as it turns out, we can use these same parallel matrix calculations to build and use neural network algorithms. So, for instance, taking subsets of words and characters, etc., and taking counts and so forth of those, and then combining them basically through multiple matrices sitting on top of each other to create vector representations over and over again. Now, we don't just have to do that one after another for each of the matrices, we can do these over hundreds of matrices simultaneously. In fact, we can see how the big effect that sort of this new technology has had compared to the age of the technology, the algorithms themselves, by sort of looking at various things that have occurred in the field. So for instance, if we take a look at how much GPUs were used among teams, how much deep learning was used among teams in recent competitions for image processing, vision comprehension. We can see, for instance, sort of, at first, nobody was using it, despite the algorithms being there. And then when we start having the introduction of GPU-based libraries like, TensorFlow, Caffe, Torch, etc., there's suddenly a huge jump up in the number of teams that are using it in 2015, and it just keeps going up in 2016 and beyond. And GPUs having thousands of cores, of course, is only one of the advantages compared to CPUs in terms of being able to work in parallel. So GPUs use plug-and-play technology. They're PCI boards that you can stick into a computer. So for instance, while for each CPU you either need a customized board or individual motherboards, HDD space, and so forth for every CPU you have, for GPUs, you can basically plug in up to 4 of them in a single box. So now, for instance, in one server, we can have one server that you can buy from any individual motherboard just about, or consumer available ones. You cannot just have 3,000 times the processing, you can have 12,000 times the processing. And this sort of similarly extends out to parallelism in the cloud. So the same kind of parallelism is sort of what has fueled the birth of cloud computing. Things like MapReduce or Hadoop or Mesos or Spark or Kubernetes. Different libraries, network libraries that have been built on top of each other one after another. So when we talk about cloud computing, sort of what we're really talking about is a cluster of network computers with the programmatic means of assigning resources across multiple machines to complete different tasks. So, just as machine learning has us taking advantage of distributing tasks to multiple threads or CPUs, so GPUs, just as we have the case of extending different tasks to CPUs or GPUs, we're doing the same thing in this case with cloud computing, but instead we're just doing it at a macro level with different machines. So the basic idea is that every computer is networked into a cluster and becomes its own node, which, much like their individual CPU cores, have jobs and sub-jobs assigned to them. So just like in the neural network where we had all that pool, and just like in the neural network where we had the pooling step that combines each of those jobs, we have individual nodes transferring data to a master node, which then collates the work together into a single piece. It was basically the exact same idea, but again, instead of taking advantage of a single machine with multiple threads, we're taking advantage of multiple machines and having one sort of serve as the center machine that's taking advantage of all of them. So coming back to our original point, where we were talking about the 100 million records, sort of the initial example. Let's say that we want to determine if a page is appropriate or not. So each record takes about 5 seconds to annotate again, yes, no, simple binary choice. And if we take sort of the 12,000 times the speed that we have, if we just have one GPU box with one GPU box with 12,000 times the speed, where we basically have 4 GPUs in it, and we take that 5 seconds per decision that a human would take. Now we've gone from 15 years to 11 hours. And in actual production, in fact, the computer can actually learn this much faster a piece than 5 seconds a record. And so, for instance, for 100 million records, it only takes half a day to learn that many records in an actual setting, as opposed to 11 hours that we were discussing as a thought experiment. And then for those yes or no questions, or 1,000-way classification task, on all those hundreds of million data points actually only takes a few hours to decide. So not only labeling things, but actually learning from things becomes massively faster once you have a computer involved. So basically fractions of a second per piece of text out there. And that's sort of just on one thread again, with one computer that has 4 GPUs in it. And so once again, we can sort of extend that again, then start multiplying that over multiple threads, multiple GPUs, and thousands of threads on their own, and dozens of machines, and so on and so forth to speed things up. So coming to a conclusion, now of course, this is to say that this isn't everything that's gone into sort of the growth of technology. There's new implementations of existing algorithms that were involved with these things. New combinations of existing technology. So yes, new implementations of existing algorithms were involved in this, new combinations of existing technologies, new research on modeling and networking, etc., all came into this as well. But parallelism is sort of the one secret sauce that allowed for the growth of the data science, and allows businesses to use these massive amounts of data that we have now. It's because we could start splitting over multiple machines, sort of having multiple packets being done at once, that we could implement more complex algorithms, combine different algorithms, and learn from billions upon billions of words in a single day. So if there's sort of one thing I want to say from this talk, it's basically take advantage of all your resources. New libraries and new technologies are all about taking advantage of all your resources in any way you can, and then using that to extend beyond what existing technologies have been. And that's the end of my talk. Thank you very much. Apologies for the gobbling.
Okay, we'll start the Q&A session. Does anyone have questions?
Thank you for the talk. If we are talking about GPU parallelism, we can now easily add a second GPU to get double the processing power.
Yeah.
But most mainstream motherboards only have 16 PCI Express lanes. So if you use 2 GPUs, then each of them will only get 8 PCI Express lanes. And in gaming benchmarks, if we drop the PCI Express lane from 16 to 8, it doesn't really affect the performance. But my question is, in machine learning application, does the PCI Express speed prove to be a bottleneck?
So yeah, in those processes, there's sort of two bottlenecks. Bottleneck one is the number of PCI lanes you have. The truth of the matter is that for a lot of existing deep learning libraries, they don't actually necessarily process at a rate that's fast enough to take advantage of all the PCI lanes yet. So you can basically use half PCI lanes that the existing 3.0 technology, PCI 3.0 technology uses, and still get similar performance. The other big issue is CPU only has 40 PCI lanes it can basically connect to, so you're limited to 4 from that as well. Any other questions? Okay, thank you very much.